Hey guys, it's Rylan, and I'm going to be talking about thorium-based reactors for my current research presentation. I first came across the idea of thorium-based reactors in 2011. I watched a TED Talk by a man named Kirk Sorensen, who was talking about using thorium reactors for lunar colonies. It was very interesting. I usually show this TED Talk every year to my chemistry and now my physics students to talk about where we can possibly go in the future. And so I thought this would be a perfect opportunity to kind of look at what research has been done since that 2011 TED Talk and what progress we've made in terms of using thorium for our fission reactors. So the three articles that I ended up using for this are nuclear power from thorium, different options, the role of thorium in the Indian nuclear power program, and then liquid fuel molten salt reactors for thorium utilization. I liked these three articles because the first one is going to be more just, it was an overview of where we are in terms of our current thorium technology and ways that we could utilize this going forwards. And then actually it mentioned several different examples in terms of the Indian experimentation, and so that's where I was able to find the second article. And then talking about molten salt reactors, I was able to find this third article from that. So this first one was kind of a jumping off point for everything else. All three articles are going to basically start with why should we move to thorium, or why is thorium a viable alternative to uranium. The biggest thing that they mention time and time again is that thorium is going to be widely more available than uranium in terms of resources in the ground. So if we look at a map of the United States, we can see that there's large thorium deposits out in the Midwest and in the Rockies over here. And the United States is usually maybe third in terms of thorium reserves in the ground. India is usually first, has millions of tons of uranium, or not uranium, but thorium in the ground. So if they can use that for their fission source, they have a very long-lasting source of fuel. Another advantage is that thorium cycles can become self-sustaining over time. So it's what we call breeder technology. We're able to produce more fission material than we utilize in our reactions. And so that's going to be advantageous because we can keep our resources up in terms of our thorium supply. Next, we're going to have a reduction of our nuclear waste burden, so the amount of waste that we're producing, or really even the toxicity of the waste that we produce. The toxicity of the waste produced by the uranium-thorium fuel cycle is going to be a lot less than what we currently have, which is up here represented by this black line, our uranium-235 and our plutonium fuel cycle. There's the possibility of higher energy output with thorium reactors. We're going to measure our energy from these reactors with something called burn-up. Think of it as a large version of the kilowatt hour. So that unit that is on the side of your house on those meters and what you're charging your bills for, we're going to be talking about, instead of kilowatts, gigawatts or megawatts, and instead of hours, we're talking about days. So that's what we're measuring in terms of our energy output for these reactors. Another advantage is that thorium is going to be very difficult to weaponize, whereas uranium is not. And then thorium reactors have the possibility of being a lot safer and a lot smaller, so we can reduce the footprint of our thorium reactors. After talking about the advantages of thorium usage, all the articles are going to go into the different possible reactor types. All those reactors can be kind of boiled down to two different types: solid fuel or liquid fuel reactors. In the solid fuel reactors, we have really three main types. We have pressurized heavy water reactors and light water reactors. Think of those as the reactors that we're currently using with our uranium technology, and we could just very quickly move over to use thorium for that. This advanced heavy water reactor, I'm going to go into a little bit more detail in just a few minutes. That is what is being proposed to be used in India with a thorium fuel. And then the other option, this liquid fuel, there's really one type, and that is a molten salt breeder reactor. So with this pressurized heavy or light water reactor, the main feature here is that we're going to have heavy or light water. So heavy water is water that has deuterium instead of hydrogen in it. And then light water is just regular water. We're going to use that as a moderator. What a moderator is, it's sort of like a barrier. It's going to slow down neutrons that are being fired into our fissionable material. And then we're also going to use this water as a coolant. And that coolant is actually what is going to take the heat generated from the fission reactions and then move it over to eventually turn some turbines. The big advantages of using these types of reactors with thorium is that we can actually just replace our uranium fuel with thorium fuel and not really have to change too much else. And then there's another advantage, would be possibly be able to produce more energy, and we already talked about that we can possibly have higher burn-ups with thorium. Disadvantages of using this type of reactor is, since we are still using old reactor types, we're going to have these larger footprints. So we're still taking a lot of space for these reactors when there are better options available. We will need to update what we call the cladding, and that's going to be kind of the barrier around the different fuel pins inside of the reactors. Since we have these higher burnup rates, we need a higher metal casing essentially. Because we're working with these older types of reactors, we're still working at very high pressure conditions. So there's always a possibility where that pressure has to go somewhere very quickly and we could have a big issue. And then since it is a solid fuel, there are still meltdowns possible. The advanced heavy water reactor, this is being proposed to be used in India, and this is what a lot of that second article was about. Some key features of this type of reactor is that it is still a pressure reactor, so we still have that pressure issue. Instead of using just heavy water or light water, they're actually going to use a combination of both of them. So the heavy water is going to act as the moderator. So it's sort of the barrier for those neutrons to slow them down a little bit. And they're going to use boiling light water as the coolant. They're going to use a mixture of two different oxides. So you have a thorium-uranium oxide and then a thorium-plutonium oxide. There would be a mixture of that for their fuel sources. Some really cool things with this is that most of the power should be generated from that thorium oxide. They are saying upwards of 60%, if not more, would be generated from that. And then there's going to be increased safety over traditional pressure water reactors. And the reason why is that they've developed this natural circulation of the coolant. They're using these gravity pools to make sure that the water continues to circulate so we don't have a buildup of this energy and cause a possible meltdown down below. So you can see in this diagram here, you have these two pools of water, and they're actually going to be able to continue to force water to circulate so that we don't have a buildup of heat and then possible meltdown down here if it gets too hot in that reactor. The last type of reactor I'm going to talk about are the molten salt breeder reactors. That's really what the third article focused on. The big main feature of this is that the fuel is now in the molten stage instead of the solid state. And it's going to be a mix of usually 4 different molten salts. There are several advantages that are kind of cool for this type of a reactor. So the first one, and really important one, is that there's no threat of a meltdown like there is in solid state reactors. Because the fuel is already in the liquid state, it can't melt down. And since there's no meltdown, it's very possible, or there's less likelihood of there being any seeping of this radioactive material out into the environment. Another advantage is that there's lower energy requirements for these types of reactors. So I don't have to put as much energy in the first place, and so I'm going to have more efficiency with these reactors. These reactors can be a lot smaller than our normal reactors, so I have less reactor footprint, and I also need less material to get it started. These reactors can operate at ambient pressure, so we're no longer working in a high pressure situation like the other 3 reactors were. And then we have fuel drainage that we can have for safety reasons. So we can drain the fuel if something goes wrong. We can store it in underground tanks until we're able to fix the problem and then reset everything. The big disadvantages of this type of reactor are going to be that the core and the coolant structures are going to have to be replaced more often, which is going to add to the nuclear waste. And then currently we just need better materials to hold the molten salts. So we don't have to replace them as often. And you can see in this diagram here, this is what the molten reactor would look like. Here's the actual reactor. Here are those emergency tanks down here. And we're just going to go through some heat exchange systems where we're taking the heat produced from the fission reaction and then transferring that heat over to a different salt and then over to water and eventually turning that turbine. So all the articles end with where do we go from here? And really it boils down to 3 main goals. First, we have to try and introduce the thorium into our current power-producing nuclear reactors or try and build up our supply of uranium-235, what we're currently using. The second thing we need to do is build up our supply of uranium-233. That's what we're going to use in conjunction with the thorium. So if we have more of that, it's going to be able to be efficient more quickly. And then lastly, we need to develop reactors specifically for thorium usage, and that's going to get back to that advanced pressure reactor and then the molten salt reactor. Using in the classroom, I think there are kind of 2 ways that I could use this in the classroom. So it's going to be in the physics classroom. I want to kind of be able to tie it back into the nature of science and also just literacy in general. Here are the standards that this would align to. So 9th grade physical science and then the physics and the AKS, that's the Gwinnett standards for that. So with the nature of science, that's really something that I try and have my students leave my classroom with is a better understanding of what science is. And I think this would be a really good way to kind of bring that in. There are several tenets of the nature of science that would tie nicely into this. One of them being that science is creative. If you read through these articles and many other articles on thorium reactors, really any of the nuclear power, you can see that these people have to be so creative to come up with these ideas for how we can utilize and how we can change what we are currently doing into something that is more efficient. Another thing that you'll see is you could talk about science being subjective. If you read these different articles, they all have their own agendas. The article from India really pushes that the advanced heavy water reactor is a better option than the molten salt reactors, whereas the molten salt reactor reaction says that that really is the way to go going forward. So you can talk about it in terms of that, talking about how science is subjective in terms of who is writing it. They're going to have an agenda they are trying to push on. So I think there's a really good way to tie in the nature of science with what the students are able to read through these different articles. You could also tie in that there is really no set scientific method. If you read through the articles, a lot of them are doing mathematical modeling to see how these would react, because these are all hypothetical scenarios. Not a lot of this is being done tangibly. It's all hypothetical at this point. And so they're not doing, the observation and then the hypothesis writing and then data collection. They have their own kind of sets, but there's not one set method that someone has to follow for that. In terms of literacy, I want my students to be able to read, write, speak, and listen on any topic that I cover in my class. And I think this would be a really good thing, a really good topic for them to be able to do all that on very easily. So they could read these articles or ones that are a little bit more suitable to their level to see what options we have going forward for nuclear energy. They could write about it. They could speak, and they could also listen to others as they talk about their ideas. And I think the ways that I could do that would be to do some type of research essay or some type of critical writing on this type of nuclear energy compared to what we currently have, or compared to fusion if I wanted to bring in fusion and talk about what fusion is. And then I could bring back sort of, no, I don't necessarily want to do the town hall like we did in class, but do some type of role playing or some type of debate where they have to take up a position and defend it with data that they are going to get from doing some research or doing some reading in those articles. So I hope this was at least a little bit enjoyable. There are my sources. And thank you for listening. And I'm sorry, Dr. Cortez, that I went a little bit over time.